Hey guys, it's the Techie Biochemist coming at you with another tutorial. Today we're going to pick up where we left off with the simulation of a protein in a water sphere with NAMD and go into a pull or force simulation also through NAMD. So the way we're going to do this is we're going to come in here and actually generate a new PDB and PSF off of this. Actually, all we have to really do is write a new PDB. So to do that, we're going to go in here to TK console. We're going to say set for here atom select top all. An important thing here is that this is with it at step 11. Why we're doing that is that since we've run this through one simulation, the atoms have now moved around in position so that none of them are overlapping. And so the position of the atoms is the data that our PDB file contains. So we want a new PDB file where all of the data on the overall protein is the same, but the exact position of the molecules is from them having been in a simulation where they got to move around freely and stuff. So this time we're going to say we're going to say $ for here, write PDB. We're going to say for here water sphere S11 for step 11 dot PDB and hit enter. And now we have that file here. So that is going to give us the necessary data we need. So I'm going to close out that one and load in the one we just created right here. The representation is different because I haven't adjusted representation settings, but this is the same protein. And so I'm then going to load in the PSF file for it, which is actually going to be the same solvated PSF we used last time. So the PSF file does not change. All right, so the next step we're going to do is come into TK console and say set all atoms select top all. The reason why we have to run this command again is because this was for the last protein that was open and we've opened a new one. So we need to run the command again. We're using all atoms this time just to make clear what we're doing. And then we're going to say all atoms set beta 0. Excuse me. Next we're going to say set fixed atom select top open quotation marks res ID 1 and CA. What this is doing is it is defining our selection as an atom that is in the first residue and is CA, that's alpha carbon. So we are specifically selecting the alpha carbon in res ID 1. And so if I were to display this graphically, let's come in here to representation. We're going to say protein. Let's make it bonds to be a little more clear. And then we'll create another rep and we're going to say res ID 1 and let's try that again. Res ID 1 and CA. Oh, name CA. Sorry. It needs to be name CA. Okay, we're going to try it one more time. Res ID 1 and name CA. There we go. Down here, we're going to change it to van der Waals. And there we go. Okay, that's way too big. So let me bring it down a little bit in size. But there we are. That right there is specifically, and if I make it invisible for a sec, we can more easily see what I'm kind of displaying there. That is the atom that we are selecting with this command. And let me just change that so we're actually typing in the correct command. All right, so now we've selected that atom as our definition of fixed atom. Now we're going to type fixed atom set beta 1. What does this mean? It means we first made all of the atoms in this entire system. We made their essentially fixed position flexible so that they can move around. And now we're saying this is the only one we want to hold in place. We don't want this one to move, whatever happens. So this is now going to be kept in place during the simulation. Now we're going to do kind of the same for the other end of the protein. What we're going to do is now we're going to come in here and figure out what the last residue in this protein is. In this case, it is, okay, these are all probably going to be waters. Oh, but we have a massive number jump here from 49. It looks like it's all cohesive from 1 through 49, and then it starts jumping. So that's probably the actual last residue on our protein. So we're going to say res ID 49 and name CA. And there we go. Yeah, that does appear to be the alpha carbon on our very last residue there. Perfect. So that is going to be the selection we use. So we're going to say set SMD atom select top res ID 1 and, or sorry, res ID 49 and name CA. Name is still CA because we're still selecting a carbon atom. Now we're going to type all atoms set occupancy 0, and then SMD atom set occupancy 1. So this is now this carbon atom that we selected is now going to be the one that gets actually affected by the forces NAMD is going to do here. And then finally, we're going to write a reference file. We're going to do that by typing all atoms, write PDB, and we'll say for here underscore ww underscore eq dot ref. That file should now be in here. It sure is. Beautiful. And so we are now done with VMD for the moment. Oops. Close that out. All right, now we are going to come into NAMD itself again, and actually I'm going to move this PDB file that I made along with that ref file I made into NAMD, because we are going to be using those files to make this magic happen. And just kind of to keep stuff from getting a little too confusing in this folder, I'm then going to select that along with the PSF file I need. And I am going to drag all of those into 3.2 pull CF there. And then I'm going to drag the configuration file for this up a level. So it's in there. Actually, hold on. I'll undo that. Control C to copy, and Control V to paste. Okay, so these are all of the files I'm going to need to run this. Just a quick review of what each of these files are. This is going to be the configuration file that the NAMD program is actually going to read in order to define what exactly it's supposed to run. This is our PSF file. This is our new PDB file that we generated from the last frame of our water sphere equilibration, so that we know that we're not having any atoms overlap, like they've actually been kind of moved around a little bit. And this is that reference file we just made that properly defines everything. So we are going to rename this real quick for here, www.pcf. Then we're going to open it up and edit stuff a bit. So the first thing is we do not need to navigate in this file up to the common folder, or up a level and then over to common and all that jazz. No, all we need to do is stay in this folder, and our PSF file is, whoops, PSF file is solve underscore for here dot PSF, and our PDB is for here water sphere step 11 PDB. For output name, we're going to say for here www.pcf. This is fine. That is the proper location of our lipid thing. And down here for our cell basis vector stuff, we're going to change that around based on the dimensions of our protein. I'm just going to set all of these to 100. That should give us plenty of room without having to get too specific. And now I need to change the reference file. In this case, it's just going to be this for here underscore ww underscore eq dot ref, and constant force file is going to be the same one, so it's going to be for here ww eq dot ref. And I'm going to decrease this to only 2,000 steps because I do not want to leave my computer trying to run through to 20,000. And this should be everything we need to run it. So let's save it and then go ahead and get this running. So we're going to type cd tutorial /NAMD. NAMD2, and then we're going to navigate to 3 to pull CF, and the name of our configuration file specifically is for here underscore ww underscore PCF dot configuration. That dot just tells it we're looking. Actually, I think we can remove that dot. Yeah, there we go. That should properly navigate us to where we need to be here. And then we're just going to make sure that we write all of our stuff to a log file, so if anything goes wrong, we can find and refer back to it. So we'll say for here pcf.log, and the command with an ampersand. There we go, and hit enter. I'll try taking out this slash. There we go. There it is. Oh, and that was really, really quick. So, all right, so if it's that quick, you know what? I'm going to go back into my back into my configuration file here, and I'm going to tell it actually to do 50,000 steps if it was that quick. So we get more total. Add 2 there, just so I know it's the second one. But yeah, I'll run this again, and that way we get one that's a lot longer. So a lot of these files are just going to be overwritten, but that's fine. Since I told it to do 50,000, it is going to be working on this for a while. So I'm going to pause my recording, and I'll see you guys back once it's all done. All right, and I'm back. Looks like this has finished, so let's open up my log file and just confirm that. And sure enough, we have the end of file stuff. So it looks like we were successful. So now we're going to go ahead and open up VMD again, this time with our new DCD, and we're going to see what our new video looks like. So file name, so all this stuff is going to be in 3.2. So there's our PDB. We're going to open that up. Get our PSF opened. And finally, we will grab our DCD, which is right here. There we go. All right. So here's our display. I'm going to just pull main in here. And whoa, okay, so this thing is getting really stretched out. Wow. And the waters are flying off everywhere. But, all right. Let's go ahead and watch this, maybe with a little slower. Put almost minimum speed, and we'll go ahead and hit play. And sure enough, we can see that thing stretching out. Wow, okay, that's really, really cool. But let's change the representation so we can actually see what's happening a little bit easier here. To do that, I'm going to say let's see here, what was it? Res ID 1 and name CA. Oops. And we will change this to van der Waals with coloring method being res name. There we go. We can see that decently well now. And then I'm going to also do that for res 49. There it is. There's our the other end of our protein. And finally, I'm going to say protein, and I will put it on new cartoon. Oh, protein, whatever. It doesn't really matter if it's on new cartoon. All it's going to show is protein anyway. And I'll make the coloring method be just name. Yeah. All right. And finally, yeah, I'll go ahead and watch the waters too. And so that will be water. For this, we'll need to go back to van der Waals, but I'm going to make those waters pretty small and transparent. Okay. Now from the beginning again, let's zoom in here a little bit and hit play. See what happens. Yeah, and so we can see this one is held in place just like we were expecting, and the other one gets dragged away by increasing force. And interestingly, we can see how the center part of the protein seems to have much stronger bonding. So even though you've got like a length here and a length here that are able to pull away and stuff, the center part of the protein is very resistant to stretching, as is this little bend here. So that's pretty interesting, that we've got some pretty strong forces at work here, and it's still not able to completely unfold this protein, even over a pretty long simulation. So yeah, a few waters are drifting off, but a lot are being held in place by, I guess, just the polar forces on some of those residues. And here we start over again, but yeah, I think that simulation worked really well. Thanks for watching. Give this video a thumbs up if you found this helpful, and comment below if there's more stuff you'd like me to cover on how to do in these applications.